Greetings! Welcome to Electronics 2. This is lecture number 45 and the last lecture in this series. Today we will finish up the study of stability, or rather instability, in negative feedback systems, and in particular talk about two important concepts. One is the phase margin and the other is frequency compensation. But before we go there, let's just review and see what we have learned about instability. We started out with a generic feedback system where the feed-forward amplifier has some sort of transfer function, some poles and zeros. And we saw that for the system to oscillate, these two conditions should hold at one frequency, omega 0. We see that the magnitude of the loop gain is 1 or higher, and the phase shift around this loop associated with H and K, as I start from here and here, is 180 degrees. So to avoid oscillation, to ensure stability, you want to make sure that these two do not happen at the same frequency. And after we study different cases, we realize that for the stability, we need the magnitude to reach a gain of 0 dB at a frequency lower than the frequency at which the phase reaches 180 degrees. In other words, the gain crossover frequency should be less than the phase crossover frequency. Okay, so that's what we need for stability. All right, and last time we looked at a two-pole system and we saw that it was stable. So if I buy a two-pole amplifier and place it in here, the feedbacks and close the feedback loop around it, it will be stable. We also saw that a one-pole system is stable. Now we're going to look at a three-pole system. So let's look at this example and see. All right, so that's perfectly natural. I take a three-stage amplifier. So here's a three-stage amplifier consisting of common source stages or common emitter stages, whatever you want, doesn't make much difference. And these have some load capacitance at the output of each stage. Let's not worry about other capacitances. So we call this R1, C1, R2, C2, R3, C3. And then these are M1, M2, and M3. So I buy this amplifier and I place it in a negative feedback loop. So I take this output, give it to K, and return this to the input. Okay, so that is the closed loop feedback system. And of course, when I say negative here, I have to be careful. You can see that at low frequencies, these three stages actually have inversion, one net inversion, right? This inverse, this inverse, this inverts. So in that case, if K has no inversion, this should be positive for the feedback to be negative, right? But we don't worry about those details for now. Okay, so we are curious to see if such a feedback system will oscillate when we have a three-stage amplifier serving as the feed-forward system. All right, well, as usual, we have to construct the magnitude of KH and the phase of KH as a function of frequency, and then examine these points and see the relative values of these two frequencies, right? So let's do that. I need more room, so I'm going to go up here and construct these. Okay, so I will plot a 20 log of magnitude of KH as a function of omega. I have three poles, so they have some values, right? So let's say, for example, we have 1 over R1 C1. That's the first pole. That's the second pole. And that's the third pole, R3, C3. Okay? So we want to plot the magnitude. This is something we studied in frequency response a long time ago, right? Okay, at very low frequencies, the capacitors are open, let's assume k is 1 for simplicity. So we're just plotting the magnitude of h, this guy, right? This is h from here to here. And we know that that would be just the low frequency gain. So GM1R1, GM2R2, GM3R3, all multiplied, right? So at very low frequencies, that's what we have. So I'll just say GM1R1, GM2 times R2 times GM3 times R3. Okay, that's the low frequency gain. Now we increase the input frequency, so we're applying a sinusoid and with a higher and higher frequency, and we reach the first pole. So Bodhi says that now we need to deflect the slope by minus 20 dB per decade. So we go like this. And then we reach the second pole, we deflect by another 20 per decade. So like so. And then we reach the third pole and we deflect by another 20 per decade. It's hard to draw these, as you can see, but you get the message, right? So this is minus 20 dB per decade, this is minus 40, this is minus 60. All right. Okay, so that is the plot of the magnitude of the loop gain. Now we need to plot the phase. Where in this plot do we have the gain crossover frequency? Well, this is the 0 dB axis, right? 0 dB. So this would be right here. So that's the gain crossover frequency. Okay, let's go ahead and plot the phase. So the angle of KH at very low frequencies, the capacitors are open, there's no phase shift, so we have 0. And Bodhi says, right at the first pole frequency, we have a contribution of minus 45. So let's just mark these on this axis, minus 45, minus 90, minus 135, minus 180. I'm going in steps of 45 degrees, minus 225, and minus 270. All right, these are all degrees. Okay, so at the first pole, we have minus 45 right here. And at 1/10 of that frequency, we begin to feel it. So we go like this. And at 10 times this frequency, we are approximately at minus 90. So at minus 90, which would be here. And the same story happens for this pole. So at 1/10 of that frequency, against the log scale, we begin to feel it. At the second pole frequency, we have reached minus 135. We got minus 90 from the first one, minus 45 from the second one. So we have reached minus 45. We continue at 10 times this frequency, we are approximately at minus 180. Minus 90 from the first pole, minus 90 from the second pole. So here is where we are at minus 180. And then for the third pole, same situation happens. And we have, let's go back to these colors here. So again, we begin to feel it at 1/10 of the frequency. We are at minus 225 at the third pole frequency right here. Right? And then eventually we asymptotically approach minus 270 degrees because each pole contributes minus 90 degrees. All right, so that is the frequency response or the magnitude and phase response for the loop gain, KH. All right, so we go back and look at this. It says that the gain crossover frequency, this one, must occur before lower than the phase crossover frequency. Is that true? So here we go. Let's change the color to black. So where is the phase crossover frequency? I follow minus 180, I hit this plot somewhere. I have to hit it, right? Because this plot is headed to minus 270, so obviously at some frequency it does cross minus 180 degrees. So at that frequency I have this, and this frequency will be the phase crossover frequency. So in this example, we see that if I have an amplifier like this, with this type of characteristic, and I place it in this negative feedback system, this negative feedback system will oscillate, right? Because we see that the phase crossover frequency is lower than the gain crossover frequency. The condition of stability was the other way around. So this system will be unstable. So again, I want to emphasize that what we are plotting here is for the open loop system, and the open loop system characteristics decide the fate of the closed loop system. They decide whether the closed loop system is stable or not. Okay, so that's an interesting example. So what we see is that for a one-pole amplifier or one-pole system or a two-pole system, we did not have any stability problems, if you remember from the last time. But for a three-pole system, we do have a problem, right? It can become unstable. All right, next example. So this is in fact a quiz for you. What happens in the previous example, in the example with three poles, if K is reduced? So we had assumed K was 1, right? So let's suppose now I reduce the value of K to 0.5 or 0.2 or 0.1, something I want. So we would like to see what happens to this system, right? And what can we predict about the stability of this closed loop system. I'll give you 1 minute to think about it. All right, so what do we decide? Okay, well, let's change the color of our pen, and then we'll superimpose on these plots the behavior with a lower k and see what happens. Okay, so I'm going to reduce k, right? So k was, let's say, 1, now it's 0.1. What happens to this plot? This is a log scale, right? So this is log of k plus log of magnitude of h. So if k goes down, let's say, by a factor of 10, then this whole plot is shifted down by 20 dB, right? So there's only a vertical shift in this entire plot because we're looking at log-log scales. So for lower k, we have something like this, right? The pole frequencies don't change, the slopes don't change, right? So it's just that there's a vertical shift. So this is with lower k. Okay? All right. What happens to the phase plot? Nothing, because k doesn't have any phase contribution anyway. Remember, we talked about this. We said k is just like a resistor or something. So the phase that we are plotting here is really that of H. K doesn't have any phase shift. So this phase plot does not change. All right, so now what happens in terms of stability? Are we closer to stability or are we farther? Well, you can see that now the gain crossover frequency is here, right? So the phase crossover frequency is here. So by reducing K, I managed to move the gain crossover frequency to the left. And if I do it enough, the gain crossover frequency will be lower than the phase crossover frequency, and that meets the stability condition. So one approach to stabilizing a negative feedback system is to reduce K. K determines the strength of feedback. If K is 1, we are returning all of the output back to the input. It's a very strong feedback loop, right? It wants to make the output an exact copy of the input. If we reduce K, if we make the feedback weaker, we are reducing the loop gain, right? We reduce the loop gain, we make the feedback weaker, and the system becomes more stable. So that's one approach. It may not be very good, but that's one approach. Okay, second example, let's write it here. So we say more stable, right? The system is more stable. Let's go to the next example. So we're still looking at this previous example with a 3-stage amplifier serving as the feed-forward system. We ask, what happens if C1 is increased? Okay. I go ahead and I increase C1, and I would like to see what happens. All right. So this is a little more complicated because as I increase C1, two things happen. Number one, the magnitude is affected. So let's go and look at that carefully. So C1 is increased. I will change the color of my pen to maybe this color. So C1 has increased. So this pole has shifted to maybe over here. So we call this omega P1 prime. This is we call this omega P1. So omega P1 prime. We increase C1. So the first pole ended up here. You can see that I increased it a lot. So it's over here. So let's try to redraw the magnitude plot for this new situation. Okay, so no problem. We're still over here at low frequencies, and we reach the first pole. We begin to go down, right? Okay. We begin to go down at what slope? At minus 20 dB per decade. So this slope is the same as this slope. So I'm going down in parallel with this. All right, so I go down in parallel with that. Up to where? Up to the second pole. Right, from the first pole to the second pole. And then I have to deflect by another 20 dB per decade. So the new one will be in parallel with the old one to the third pole, and so on. So the first pole changed because C1 increased, but the second and third poles did not. So that's the new response of the magnitude of KH. All right, if K, for example, is 1. K didn't change, just C1 changed. Okay, now let's go back to the phase profile and see what happens there. It's a little more complicated now because the pole frequency has moved. So the phase profile will change. All right, but no problem, we'll just take it slowly. Okay, here's the new pole frequency, the first pole. So what we have to do is we have to cross minus 45 at this pole frequency, right? So we get something like this and like this. So we have minus 45 at the first pole, about minus 90 at 10 times this pole, right? So it stays at minus 90 for a while until we get to the second pole right here. and then it just follows the old plot. Do you agree? Only the first pole changed. The second and third poles did not change, so the phase profile does not change around here. It's just that this change of minus 45 doesn't happen at this frequency, it happens at this new first pole frequency right here. Okay, so far so good. All right, so what happens to the stability of this overall system now that I have increased this capacitor? All right, so again, we go back to this condition and see. Where is the new gain crossover frequency? The new gain crossover frequency is here, right? So that's the new gain crossover frequency. So all these colors are related to each other, right? This purple color is used for when we have the lower pole frequency here and here and here. All right, and where is the phase crossover frequency? The frequency at which the phase reaches minus 180 degrees. Well, that doesn't really change, right? It's still here. It's still here because it was really this part of the plot that changed. Sorry, not here. Not here. It's at 180. So let me erase this quickly and reconstruct this part quickly. And then we go back to this plot here. So it is this point. This point hasn't changed, right? Because we changed this part of the profile. But at this point, we are so far from this pole that it doesn't matter whether the pole is here or here. The total phase shift at this frequency is still minus 180 degrees. So we see that the phase crossover frequency did not change, at least not much, whereas the phase crossover frequency went from here to here. The phase crossover frequency, the gain crossover frequency went to the left. So it becomes more stable because we want the gain crossover frequency to be to the left of the phase crossover frequency, right? And this is what's happening here. So interestingly, I could also increase C1 to accomplish stability, right? So system more stable. And these two examples really capture the essence of all negative feedback systems that we have. So in circuit design, so we have to do one of these two things if the system that we have built is not stable or not stable enough, right? So you took some sort of amplifier, placed a negative feedback loop, and then you constructed the open loop characteristics and realized that, yes, the gain crossover frequency is actually higher than the phase crossover frequency, so that's no good. Now we have to figure out what to do. All right, these are just some examples. Okay, let's go to the concept of phase margin and see what that means and why it's important. So we're going to talk about phase margin here. And I wanted to just give a quick note on stability test. So if I give you a closed loop feedback system like this, and you're not allowed to open the loop, okay? And I say, test this for stability. What do you do? All right. Well, we saw that with the sinusoid at omega 0, we were getting a very large amplitude at the output. The gain from here to here was infinite, right? So, but I don't really know what frequency that is. I have to go and sweep the frequency. Alternatively, what I can do is I can apply a step here. You can think of a step as something that has all frequencies in it, right? So when I apply step here, what I see at this output could be like this, so it starts oscillating. So that's an unstable system. Or it can do something like this, right? Which means it's not very good. It's at the edge of oscillation. It's not quite unstable, but not really reliable, right? Or it could do this. And that's a nice system, right? It's a well-behaved response, so we know that the system will not be unstable. So it's always good to remember that we can apply different things at the input of the closed-loop system to check for stability. All right, so just remember that note, and let's go on to the concept of phase margin. Okay, so consider these scenarios. All right, remember the three scenarios I showed you last time? So I'll take a look at some of them again. So 20 log of kh as a function of omega, and then the phase of kh as a function of omega. And we said, well, if the gain drops to 0 dB, the loop gain, at some frequency, and the phase is also minus 180, then we have a problem, right? The system is unstable. So if I build a system like this, I buy an amplifier, that amplifier has this type of characteristic, and then I put it in the negative feedback system, that negative feedback system will be unstable. So here's, I place this amplifier right here, apply some K, and now if I give a step here, what do I see? The output will go up and down, it will oscillate. All right, is that clear? Okay. Now, all right, so that's not good. And our condition on the previous slide said we have to move this frequency to the left, right, to the left of this one, to have some stability. Okay, so let's go ahead and do that by techniques that we saw. You can reduce K, you can move the first pole towards the origin, right? By one of those techniques, I managed to do this. So I'll just say kh, knowing that this is 20 log. So I move this over here, and for the phase, I have still minus 180 here. Well, let me do this more carefully. Okay, so let's say this frequency is some value omega 1. And this is the gain crossover frequency. And the phase crossover frequency is just a little higher, right? So right here, so omega 2. So yes, the system is stable, strictly speaking. But is it good? Is it a well-behaved system? Because these are so close to each other. So if I do this test, what should I see here? So we draw that very quickly, and we apply a step again. So as you might expect, yes, it will not oscillate indefinitely, but it will have a poorly behaved behavior, right? It will go like this. All right, because these two are so close to each other. So that means that I have to have some reasonable separation between these two. And that's the third scenario. So we'll have magnitude of kh, again log, and it's somewhere around here. We call this omega 1. Then we have the phase of kh, and that happens over here at omega 2 minus 180 degrees. Okay, and these are far enough. So at omega 1, we have a phase that is sufficiently more positive than minus 180. Here, at omega 1, the phase is still pretty close to minus 180, right? But here, at omega 1, at the gain crossover frequency, the phase is away from minus 180. So in this case, what we might expect is that the closed loop system now has a pretty good behavior. So if I give a step here, what I will see is also a nice step here. All right, so that's what we would like to have in feedback circuit design or feedback system design. So now the question is, how do I quantify this, right? What number should I choose? How should I choose these numbers when I'm looking at these responses to ensure that the closed loop system will be nicely behaved? I don't want to be here, I want to be here. All right, so we have a very simple rule, and that's how we will ensure that. So let me change the color of my pen. It's a very simple and beautiful rule. So first we're going to define something. So remember that the phase at this frequency is sufficiently more positive than the dangerous value of minus 180. So this difference is a margin, right? Here the margin is very little. Here the margin is 0. Here there's some margin. So we're going to call that the phase margin. So we say the phase margin is equal to, how do I calculate that? Is the phase of the loop gain calculated at what frequency? At the gain crossover frequency, right? So it's the angle of kh of omega. We're going to denote this by something called gx. Gx is the gain crossover frequency, okay? So that's this angle, this value here. So let's say this value is minus 100. But I'm interested in the difference between these two. So I have to subtract this from this. That would be plus 180 degrees. So if this angle here is minus 100 and this is minus 180, the difference is 80 degrees. So the margin that we have, specifically the phase margin that we have, is 80 degrees. So the phase margin is a great and beautiful indication of the stability of the system. Here, the phase margin is 0. Here, the phase margin is maybe 5 degrees. Here, the phase margin is 60 degrees, 70 degrees, 80 degrees. So that's the number that we use. How much phase margin should we shoot for? So a rule of thumb is about 60 degrees. Okay? For well-behaved response. So that's a relatively universal number that people use. It's not very strict, so you can go up and down a little bit, but in most cases it turns out to be a good rule of thumb, so that we know that we have to move this frequency to the left so much that this phase, the value of phase of kh, with respect to 180 is 60 degrees away. So what we want to have minus 120 at the gain crossover frequency. So that means that this angle, the phase, should be approximately minus 120 degrees, so that the phase margin is about 60 degrees. All right? Okay. So that's the fundamental number that we need, and that's always a good thing to have. Let's see. Okay, I wanted to give you one example to see how all of these ideas come together. So here's an example. So remember the one-pole system that we looked at last time? So here's a little common source amplifier with a single load capacitor, R1 and C1. And I placed this in a negative feedback loop. So here's H, this goes through some K, and then comes back here. And now we're interested in the stability of this overall system, right? Okay, and last time we said this cannot oscillate because the phase of H, the phase of this guy, at most is minus 90 degrees, and that happens at infinite frequency anyway. So we can't possibly reach a phase of 180 degrees as we travel from here to here. Okay, that's not possible. But of course, naturally we can ask, okay, great, it is stable, but how much phase margin does it have, right? All right, so no problem, let's do this. Here we construct those plots. So magnitude of kh, and so again, let's say k is 1 for simplicity. As a function of frequency, we have something like this, right? And this is 1 over R1C1. A single pole response, so the pole is at 1 over R1C1. And then the phase, according to Bode, starts at 0. At low frequencies, there's no phase shift. And at the pole frequency, it's minus 45. And at 10 times the pole frequency, it's approximately minus 90. So minus 90 degrees. So it goes like this, and it asymptotically approaches minus 90 degrees. Okay, so we are interested in the phase margin. So first we have to find the gain crossover frequency, right? This value. The gain crossover frequency is right here. Right here. So this is the what we call omega gx, the gain crossover frequency. All right. Then we have to compute the phase at that frequency. Okay, the phase of kh. So I have to go down here and find this, right? That is the phase, this phase. Okay, how much is this phase? It's not minus 90, because minus 90 would be at infinite frequency. It's some amount, right? We can calculate that. So let's say it's minus 80 degrees as an example, right? It's not that hard, right? Because we have the equation for this transfer function. You can readily find that. But if it's minus 80, as an example, what is the phase margin? Okay, so if that's, then the phase margin would be minus 80 degrees plus 180 degrees. So it's 100 degrees of phase margin, right? More than 90 degrees. Definitely more than 90 degrees. Why? Because this phase that we calculate can never reach minus 90. Minus 90 happens only at infinite frequency, right? So when we calculate the phase at this frequency, it's always more positive than minus 90, which means the phase margin is always greater than 90 degrees. Okay, in this example, is 100 degrees. All right, so this shows you the procedure for finding the phase margin of a given circuit, given loop. We have to break the loop. We have to plot the magnitude of the loop gain and the phase of the loop gain, and then identify the gain crossover frequency where the loop gain has dropped to 1, 0 dB, and then come down and see how much phase we have, right? And then look at that phase, compare with minus 180 degrees. Very well. Let's go to the next page and talk about one more concept, and that's frequency compensation. So let's say that I have bought an amplifier, I put in a feedback loop, and the feedback loop is not stable. The question is, how do I stabilize the system? That act of stabilizing the system is called frequency compensation. All right? So here's an example. So again, remember, we might have a 3-stage amplifier. So here's our 3-stage amplifier, and it will have 3 poles, maybe even more. So here are some caps and resistors. R3, C3. And this whole thing is placed in a feedback loop. So this is H. And now we give it to K. And we go back to the input subtractor. And that's X. And that's Y. Okay, so we have constructed the system, and either we did a closed loop test. For example, we gave a step here and we saw that it oscillated, or we looked at the open loop. We broke the loop and we found the loop gain K times H. We plotted the magnitude of KH, the phase of KH, and we saw that the phase margin was 0 or even negative, meaning the system was unstable. So now we need to stabilize the system, and that is called frequency compensation. Okay, so I showed you two examples before, right, where we saw that the system became more stable. And in fact, those are exactly what we call frequency compensation. We will focus on the second one because that's the more important one. So we say frequency compensation by moving the first pole toward the origin. Okay, so the first pole sometimes is called the dominant pole, right? This is the lowest frequency pole that we have. So if you remember, the way we approached this is we said, what happens if I increase C1, right? So I wanted to increase C1. Increase C1. When I increase C1, assuming that this is the first pole of the system, of this H, then this pole will move to the left, right? And that means, in magnitude, in absolute value. And that means that we managed to move the gain crossover frequency to a lower frequency. So let me try to plot that quickly here. So imagine that I start from a system like this. Omega P1, Omega P2, Omega P3. And this is the magnitude of KH. And for the phase, if you remember, we have something like this, right? At minus 45, another minus 45, another minus 45. So this is minus 45. This is minus 135. This somewhere around here is minus 180. And then eventually it's minus 270, right? Okay, so we said that, well, it could happen that you see that the gain crossover is here, the phase crossover is here, where we reach minus 180. This is the angle of KH. So we have a problem. So this frequency is higher than this frequency. So I need to push this frequency down. And one approach is to move omega P1 to a lower frequency by increasing C1. So I said, okay, let's move this all the way to here. All right. So this is omega P1 prime, meaning after C1 is increased. And then what we saw is that now we begin to drop at this pole frequency. So we go like this, we reach the second pole, we go like this, and so on. And this part doesn't change because the slope is the same as the slope, right? And this slope is the same as this, and the third pole is here. So the key point is that we managed to move this gain crossover frequency to here. Okay, and then as far as the phase is concerned, sure, because the first pole occurs now here, the phase profile changes around here, right? Because at the first pole we should have minus 45 degrees. But by the time we get out here, we really don't see any difference, right? It's the same thing as all of that. So by increasing C1, we managed to move the gain crossover frequency to a lower value. without changing the phase crossover frequency, so the system becomes more stable. Now in this particular example, you can see that I haven't done a good job, right? This is right here. So I need to increase this capacitor even more. This has to go right here, right? If I push it to the left far enough, then eventually this frequency will be lower than this sufficiently such that the phase margin is what we want, for example, 60 degrees. So right now the phase margin is not much, right? So the phase margin is only the difference between this and this, so it might be 5 degrees or 10 degrees. So this is what we do in frequency compensation. We identify the first pole, right? The first pole. It could be here, it could be here, it could be here. And then we try to push it towards the origin by manipulating the capacitor value. And that is the interesting concept of frequency compensation. All right, this concludes this lecture series. I thank you for staying with me for 45 lectures, and I hope these lectures have been beneficial. Best of luck to you.